Hey, I'm Matthias Neu, and I'd like to describe real quick how to configure a digital input charm for the AMS Asset Monitor. So for doing so, as we're already connected to the AMS Asset Monitor box and move to the charm section, we can easily click on the charm itself, which is the digital input dry contact charm, and going into the configuration by either choosing the configuration button at the lower part, as this charm is completely not configured by now, or pressing the configuration button at the upper right corner, which is a configuration button that is always available also if the charm has been configured before. So going into there, we see at the basic section once again that we are able to disable the charm completely by the checkbox enable. So we can click the box and check or uncheck the box. Further to that, we're having description opportunities, which is, for example, just the name of the of the use case here. So I just call it DI digital input as it is used, and the cabling ID for the signal connected to the digital input finally. And the cable connected to the digital input finally. So I'm just entering any number here. Now, at the detailed section now, we see from functionality field that this charm is used for two different reasons. So the first reason, it could be a digital input charm to just detect a DI signal coming in, so high-low level detection and providing this information to internal processing. And then we're using this charm from functionality perspective as a discrete input. So if using the discrete input, we see that we have filter opportunities. And the first filter here is a debounce filter. And what we see here is that we have opportunities of none, so we can completely deactivate that. Then the output or the input will be detected for internal processing as it comes in. So short pulses are detected as short pulses, long pulses are detected as long pulses, and this is given into the internal processing finally. So with a delay filter that could be chosen, we also see that we have a value to be entered for the delay filter. That also only means that if a signal becomes true status, high level status at the input, it will wait for the number of milliseconds that has been chosen, for example 10 milliseconds, before the internal processing will detect the true status as well and process the true status as well. So that means it's a kind of delay of becoming true until the true condition will be processed. Another opportunity is the glitch filter, and the glitch filter means that it is looking after pulses as they are coming in, but whenever a pulse comes in, also for small pulses that may have just 1 millisecond or 2 millisecond width, it will always respond to internal processing with a pulse of 10 milliseconds according to the value that has been set up. So it will transform a small pulse of just a millisecond or two into a pulse of 10 milliseconds internally for further processing. And last but not least, we're having averaging filters, and they are a little bit complex. So for the averaging filters, we're looking after value that is given in counts, and that goes back to the sample frequency of the input itself. As the AMS Asset Monitor charm, the digital input charm, is sampling the signal, the input, finally with 1,000 samples per second. That means if a signal becomes true at the input, it's starting counting until it reaches its value of 10 counts, or could be more, so it goes up to 100 counts if we want to. So it starts counting the pulses as long as the input signal is true. So it starts until 100 before it moves over to or provides this information to internal processing until it after reaching the counts 100, or if we would have set up to 10 counts, it's just 10 counts. And it goes the same way, different direction. So if a signal is true and becomes deactivated or false at the input stage, it needs to count back to 0 before the internal processing detects and processes the 0 detection finally. Additionally to the debounce filter, which is mainly looking after the signal how it comes into the DI charm, we have another filter which is called the output filter that's mainly affecting the signal before it moves out of the DI charm to the internal processing of out at the backplane and further charms as well. So at the output filter we have again an extended opportunity, so that's the extend filter, and we may enter a time value here as well. That means it's looking after very small pulses that may come in of just 1 or 2 or 3 or 5 milliseconds length, and it will respond to the output of the charm with a pulse that automatically goes to 100 milliseconds that way. Further to that, we're having a delay filter, which is just a delay in processing, but we also have delay on and delay off, which is just looking after the true and the false condition. So that automatically means for the delay on, the signal needs to be on for the amount of 100 milliseconds before it will be processed as a true signal to the output. Or for the off, it needs to be 100 milliseconds in off condition or false condition before it will be provided as an information of off or false finally to the further processing. And last but not least, there is a glitch filter and a saddle filter. And for the saddle filter, that always means that a signal, an event, independently if it is true or false, or low or high, needs to be of length of 100 milliseconds exactly. And if it is detected independently of true or high, it will always change its state finally. So that means with a saddle filter, it will just do a high-low change at the output whenever a true or false condition comes with exactly 100 milliseconds length at the input or internal process signal. So additionally to that, we're able to modify our input functionality to be inverted. That means that a high signal would be detected as a low signal and otherwise, and vice versa. So this can be checked or unchecked depending on the principle how it should be processed. And last but not least, we're having line fault detection. And this line fault detection means that this is a kind of channel OK recognition. But for doing so and doing the line fault detection, keep in mind that there is an external resistor network required that needs to be connected to the input, which will do an offset of voltage just to allow the digital input charm to detect if a sensor and the loop is healthy or not. But as said earlier, there is a second functionality the digital input charm can be used for, and this is, if we're moving back to the functionality section here, it can also be used to count pulses at the input. So it's just counting the pulses and measuring the amount of pulses over a period of time for detecting the speed of the machine. So we're using the digital input charm as well for getting a speed information into our calculations. It's not a key information, don't misunderstand that. It's just counting the pulses and measuring the time. And with that, we're able to do a live understanding, a real understanding of the speed of the machine by using the digital input charm. For that, we're using inductive sensors typically. We're having some recommendations of that. Okay, so if using the functionality pulse count input, we're having an averaging time, which is not really a filter, it's just a time specification, how often the amount of counted pulses should be updated to the output as a speed information. So that only means for a period as specified over here, 130 milliseconds in range up to 60 seconds, that means that the monitor at 60 seconds would be counting pulses up to 60 seconds length and divide the number of pulses through the 60 seconds for referring with the speed information. So that means the speed information value will be updated every 60 seconds, which is a quite stable signal finally for a changing speed machine. If it is a stable machine, we can also use a lower time for the update rate. So for example, just 500 milliseconds or down to 130 milliseconds here. And we have again this line fault detection opportunity, but as said earlier, Keep in mind that this requires an external network, or external resistor network, to be connected to the input of the charm as well for enabling the line fault detection. But if we have this network connected, we can easily check the button and we will get a channel OK recognition for the type of sensor or the input signal detection available as well. And last but not least, for the speed information, but not for the DI, but for the speed information, we're having a display range again, so the monitor could count the pulses and measure the speed for very high speeds as well. But finally, it may not be required, as the nominal speed of a machine could be in range up to 3000 or 3600 or whatever. So we can adjust our scaling, our display range with the display section over here as well. So for example, let's say up to, yeah, just 200 hertz, whatever, should be shown from the bar graph and the display inside of the AMS Asset Monitor. So and that's finally everything we need to do for setting up before we're able to set up our save button, to press our save button. And with that, we're moving back to the overview page, and now you see that it is configured, but I don't have any sensor connected right now. So we don't see any speed and we don't see any line fault detection right now as the channel is open, and this is indicated. But now the color moved from purple into red, as a fault is detected for sure, but we have configured our digital input charm now. And that's quite everything you need to do for setting up and configuring a digital input charm.